Bismillahirrahmanirrahim. Dear Honorable Speaker, Research Enthusiast, Participant, good evening. Welcome to your most expected Research Ideas series. I am Mehedi and Himel, Research Ambassador of Gobeshok Hote Chai, B Researcher BD platform from Bangladesh Army University of Engineering Technology. It's my pleasure to host today's program. Before dive into the lecture, I will introduce Gobeshok Hote Chai, B Researcher BD platform, its mission, vision, and activities. B Researcher BD is an online-based, non-profit open platform directed by some world-class scholars. They are tireless working to promote research and guide young researchers in Bangladesh. Its vision is to leverage research in higher educational institute for sustainable development all over the world. This novel effort has been initiated by Mr. M.D. Sabir Hussain. He is working as an assistant professor at the Department of Computer Science and Engineering of Chittagong University of Engineering Technology, Bangladesh. Universities are the place for knowledge creation and dissemination. However, we know that the universities are going in the traditional way. Although the final year students do their thesis or project for obtaining the certificate, but research and publication at undergraduate level are rare. Mr. Sabir Hussain worked in a different way. By his effort, the second year students of the CSE Department of Chubet have published more than 10 articles in international conferences and journals. This type of accomplishment is rare not only in Bangladesh but also in first world universities. Being perplexed by this achievement, he has created this platform to diverge this enthusiasm among all of the students who are interested in higher studies. They are assisting researchers by sharing research-related resources such as book, paper, website, etc., conducting online or offline training courses, arranging seminars, workshops, or webinars, research collaboration or supervision, arranging internship opportunities. Previously, they have conducted the country's first free complete online training on how to become a researcher. This course covers the basic concept, tools, and techniques required to become a researcher from zero knowledge. The recorded lectures on YouTube received more than 23,000 views within 7 months only. Then they are going to start the most demanding online free course titled Python for Research from any discipline from 27 April 2021. We know that selecting research idea is the most important step in research methodology. However, finding a research idea or topic is challenging job for the research enthusiast new learners. To assist them in finding ideas easily, we are organizing this research ideas series. Research scholars from the home and abroad of different disciplines will deliver lectures related to his research expertise or domain knowledge. Basically, speakers will share trending research topics, skills, tools, and techniques required to start his current and past research projects. Publication guideline for a specific field. We have a plan to cover all possible research areas in future. Now, I am going to introduce today's lecture and speaker. It is the fourth lecture of the Research Idea series. The title is Additive Manufacturing from Bio-Inspired Engineering to Space Propulsion. The key highlights of this lecture are additive manufacturing in alloys and composites, skill set required to pursue research, speakers' current and previous research, how to transform a small idea to a publication, research collaboration. Today's honorable speaker is Dr. Molla Hasan, is an assistant professor at the Inamori School of Engineering at Alfred University. Being joining Alfred He was a postdoctoral associate at Rutgers. Dr. Hasan earned his PhD in mechanical engineering from Texas Tech University in 2017. He received a master's degree in mechanical engineering from Lamar University. Molla University of Engineering Technology, BAUET. In his alma mater, Dr. Hasan's research interest includes functionalization of materials, additive manufacturing, polymer composite, size effect on materials properties, and porous materials. Dr. Hasan has published more than 150 peer-reviewed papers in scholarly journals. The lecture will start on. There will be question answering session after the lecture. You can ask questions by commenting on this live program on our page or joining the StreamYard link directly. We will share a StreamYard link in a question answering session. Now, I am requesting our honorable speaker to start today's lecture.
Thank you, Mehedi, for the kind introduction. And thank you for those who are watching this webinar. And good evening, everyone. So as the speaker said, the Mehedi said, I actually, the title of my today's talk is Additive Manufacturing from Bio-Inspired Engineering to Space Propulsion. Now, before start, I would like to introduce my institution, Alfred University. It's a small university located at upstate New York. Those who are familiar with the Niagara Falls, it's a 2-hour drive from the Niagara Falls, and it's located in the upstate. It's very far. It's a 6-hour drive from the New York City. Now, today I will cover three major prongs of the first. I will discuss what we do, and the second I will try to elaborate what kind of skill set required for experimental research, and the third I will just show a couple of examples how can you transform your small idea to a publication. Now, so in the additive manufacturing is a multi-step manufacturing, and I will like to discuss the two topics. One is the how this additive manufacturing can unravel the physics of wetting, and what kind of devices we can make by using the additive manufacturing. So let's jump to my research first. Now, I would like to start this talk with a story. The story of two famous person, and the pictures you're seeing, the old man, I think everybody knows who is he. This little boy one day actually came to him and asked for an autograph, and Rabindranath Tagore told him to come the very next day. So the little boy actually went to the Rabindranath Tagore and asked for the autograph again. So Rabindranath Tagore wrote an autograph and gave it to him, and this was his autograph. So I'm pretty sure that most of you are familiar with this famous poem and this famous this quote. দেখা হয় না চক্ষু মেলিয়া ঘর হতে দুই পা ফেলিয়া একটি ধানের শীষের উপর একটি শিশির বিন্দু. Now, to me, it's a very, very powerful message. The message is, he says that the mother nature surrounding us is a very good source of knowledge. If we can explore the mother nature, if we can translate the physical phenomena, and we can not only earn knowledge, we can increase the scientific activities, and from this concept, actually, the bio-inspired engineering developed. The bio-inspired engineering is an engineering where the scientists and researchers explore the different phenomena in nature and try to mimic those phenomena uh, by doing synthesis, by doing simulations. And I'm giving you a couple of examples of bio-inspired engineering. And one of the example is very famous example is a gecko-inspired robot. The gecko can climb any vertical surfaces. Almost any surfaces they can climb, except the Teflon. Now, why? And it can, when it is climbed, basically, you know, it can climb very fast. So why it can climb on a vertical surface? The reason is the gecko feet has a special kind of microstructure. It's a special kind of topology that provide it an addition called anisotropic addition. So because of this addition, they can climb on a vertical surface. The other example is the moth. The moth can see even at dark. The reason is that the moth eye has a very special kind of topology, and this topology can trap light. So even a small amount of light is incident on the moth's eyes, they can trap. As a result, moth is able to see when in the dark. The third example I'm giving here is a shark scale. The shark scale has is not a is a very special aerodynamic shape, and because of this aerodynamic shape, when it swims, that shape actually reduces the drag force, and as a result, the drag force reduced, the shark can swim faster. And this kind of uh, aerodynamics design is nowadays implemented in the boat and ships surfaces, so that actually the drag force actually reduced. So I'm particularly interested in a research that we call wetting. Wetting is a phenomena. I'm pretty sure many of you have seen that the in many leaf the water droplet do not stick in, and it rolls, it can rolls, and when it rolls and it takes away all the dirt, and that's why the lotus leaves is always remains clean. And the if you closely examine the lotus leaf surface, it has been seen that there is a microstructures, and on the top of this microstructure there are some wax, nano wax, and it lowers its surface energy, and that's why the water does not stick on a lotus leaf. Now, so wetting is a phenomena, and wetting is defined how much in water droplet or any liquid droplet spread on the surface. And it could be liquid, it could be in a milk, it could be any oil. So how much a liquid droplet spreads on the surface is defined by wetting. Based on this definition, there are three types of wetting. We call complete wetting, partial wetting, and complete de-wetting. So let's first talk about this partial wetting. So if I put a water droplet, or a liquid droplet, it makes a contact angle in this three-phase interline, air, solid, and liquid, and this angle is known as contact angle. Now, if this angle is 0, we call it complete wetting. If this angle lies between 0 to 180 degree, we call it partial wetting. And for if theta turns to 180, it is called complete wetting. So both complete wetting and complete de-wetting both are very useful. And now, for example, in lubrications, this is an example of journal bearing. As you see, the journal and bearing, actually there is a space, and this space is filled by an oil. And when we use this selection when we select the oil, we want that small amount of oil should cover most area. So that means you need complete weighting. And this oil has served two purposes. First, it protects from wear, and it also uh, used as a coolant. The second example is painting. If you want to do paint, you want that the minimum amount of paint liquid should cover maximum amount of area so that you have a very thin film on your wall. So for these, you want that your painting should wet the surface completely. Again, on the other hand, the complete deweighting is very essential for some application. We call this artificial superhydrophobic surface. You may notice that these high-rise buildings, those are classes, are very clean, and and the reason is actually those high-rises building has a special coating, so the the dust or dirt when sticks on there when there is a raining or some kind of water spraying, and those droplets actually take away all the dirts because it rolls. Now, if you can combine these two things, like complete weighting and complete deweighting, we can actually expand the application. So, for example, this is a filter. Um, this filter is made by a membrane, and this membrane is like that. It allows water to go in, but it did not allow the oil pass through. So as a result, this membrane acts as a smart filter. So as you see, this is your oil water emulsion, and and this filter actually put this oil in this beaker and this water in the another beaker. So now weighting is a phenomena which is governed by two different parameters. The one parameter is called the surface roughness, and the other parameter is surface chemistry. Now, let me talk about a little bit about the surface chemistry. Now, the molecule at the bulk and the molecule at the surface are not the same in terms of interactions. So molecule at a surface actually misses its interaction. So molecule at the bulk doesn't need to interact anyone because its interaction is complete. The molecule at the surface misses its interaction. So that's why they want to attract. They attract the foreign particle. They attract the foreign particle. And metals like copper, steel, aluminium, they attract foreign particle very vigorously, and that's why metals are typically hydrophilic. On the other hand, the polymers are hydrophobic, like PMMA, PVDS, PDMS. Now, and this way, but so this is the surface chemistry. So if your chemistry is different, your wettability will be different. Now, surface roughness also has a role on weighting. And to characterize the surface roughness role, there are several models actually introduced. One of the famous model, this is the first model, that was a Wenzel model. And Wenzel model says the roughness amplifies intrinsic weighting behavior. Let me explain this one. So if you look at this figure, and this is a flat surface, there is no roughness. And this flat surface, the contact angle is more than 90 degree. And as your roughness goes higher, the contact angle increases. As you see this, now it's a from half sphere, it turns to almost full circle, full full sphere or circle. So that means the roughness amplifies. So theta from 90, it reaches to theta to 150 or 170. So that says that roughness increases contact angle. Now look at this figure. This is a droplet on a silicon, and this is your droplet, and the contact angle is 31 degree. And as the contact angle increases, as the roughness increases, the contact angle goes down. So if theta is equal to less than 90, we will see this kind of behavior. But if I coat this with change the surface energy by coating and then do my roughness, and then roughness, the contact angle increases. So that means that theta is less than 90 degree, the roughness will decrease its contact angle. If theta is more than 90 degree, the roughness will increase its contact angle. That actually satisfies the Wenzel model. However, so that theory was established for half a century, and in around 2008-9, some researcher actually questioned this theory because they showed that metals can be hydrophilic metals can be turned super hydrophobic without changing any surface chemistry, just simply by roughness, which is not possible according to the Wenzel model. So there are then after that actually some other researchers actually look at this issue, and they also seen the similar phenomena. So they saw that when you, for example, this platinum substrate is radiated with laser, and the contact angle changes from here to here, has a significant changes. And there are some other method actually developed: laser irradiation, chemical etching, sandblasting. Now, so the problem of this method is they lack systematic pattern surface, and the other problem is that their chemistry change when they do the pattern. For example, this iron, when irradiated with the laser, at the beginning, their contact angle is say less than 10 degree, but over the time, this contact angle actually changes. So that is very peculiar. And it turns out that at the beginning, when the piston surface, when it is irradiated with the laser, there is a non-stoichiometric iron oxide actually developed. And this non-stoichiometric iron oxide over the time react the atmospheric carbon dioxide and turns to a stoichiometric iron oxide and leaves carbon on the surface. And this carbon actually is hydrophobic in nature, and that's why the entire surface wettability switches from hydrophilic to hydrophobic. Now, the question is, can we decouple surface roughness and surface chemistry, and can we identify what is the true effect of surface roughness? Now, traditional alloy and metal is not homogeneous. So for the ideal metals to study the effect of topography on wetting, there are three major criteria. The first, the surface needs to be homogeneous and remains homogeneous after texturing, and roughness can be varied systematically from nano to micro. Now, traditional metals and alloy are not homogeneous and microscopic level. So as you see, this is the microstructures of gold silica binary alloy, and these black spots are silica rich phase and the white are gold rich phase. And this is the microstructures of platinum. As you see, these are grain boundaries, so these are not homogeneous either. So there is an alloy called metallic glass, which is very homogeneous at sub-micron length scale. Actually, sub-nanometer length scale. This is very homogeneous. This is a TEM image. As you see, how homogeneous it is. And these metallic glasses can be very easily patterned to sub-micron length. So these are the some patterns using the metallic glass. As you see, these micro holes, and these are the nano rods. And as you see, these length scales, this is 50 micron, this is 50 nanometers. So that is actually, I would say, these diameters, I would say 10 nanometer. Now, so what is metallic glass? So in the traditional steel and alloys, like traditional crystalline materials like steel and copper, what you have ordered atomic structures, and if this each minion is an atom, so in steel and copper they are in order. Some they have a crystal structures. Crystal structure is an ordered atomic structure. On the other hand, there is another kind of material we know that is called glass, and glass is amorphous. And what is this? What is the significant difference between the glass and traditional uh, alloy? One of the difference is that the glass does not have, many glasses does not have glasses does not have the ordered atomic structures. They are disordered atomic structure. So metallic glass, by it has the it constitutes of metals, but it has some characteristics of glasses. So that's why the metal is called metallic glass. So this metallic glass is invented in 1960. It is an alloy of 2 to 6 elements, and it's a very homogeneous. It's a high yield strength. I'll just give an example. The yield strength of steel is 400 megapascal. On the other hand, this PDE-based metallic glass, one of the very common metallic glass, yield strength is 1.7 gigapascal. It's a 4 times higher than the steel. And you can form very small parts with precision and by thermoplastic forming. And it's very good to against the corrosion. So this is an example of a one zirconium-based metallic glass which was soaked to a salt bath for 336 hours. As you see, there is no stain. There's no sign of corrosion. So it's a very corrosive resistance material. Now the application. So metallic glass steel is a developing metals, developing alloys. It has a very few applications. So one of the applications actually.
Sorry to interrupt. Dr. Hasan, would you please hide the small window at the bottom of the slide share?
Okay. It works. Okay. Thank you. So this is a watch. This is called Simstar 300, and this watch actually, it's a is used one of the James Bond movie that is Baxter in 2000. I don't know the year, but it is the Spectre's movie. This watch was some of the parts, especially these dials, were made of metallic glasses. And so, and these fuel cells, which is entirely built with metallic glasses. So there it has some applications. So metallic glass is the way we process the metallic glass. You can process, it is a molten state. You will rapidly cool, and so that you can avoid this crystallization zone, then it gives you glass. Once you form the glass, then there is a region called supercooled liquid, and you can actually do your forming at this region. You heat the metallic glass at a certain above the glass transition temperature, so the metallic glass gets softened, and then you can do your shaping. And basically, to pattern on metallic glass, we use mold, and we heated the metallic glass over the glass transition temperature. We press, and after that we throw the entire assembly to the KOH. KOH is an etchant. It eat away the silicon or the mold and the free the metallic glass. So this is the pattern surface. And I'm not gonna details go about these things. And so weighting of metallic glasses, some people actually reported patterning metallic glasses transform the weightability from hydrophilic to superhydrophobic, but we didn't get that result. We couldn't copy that results despite our multiple effort of with a different pattern. So we was perplexed why these things didn't happen to us, why we are not getting exactly the same results where other researchers have been reported. And so we thought about, is it possible when there is some chemistry change while we do the embossing process? Is surface get contaminated while we also perform the etching? And in order to do that, we did a systematic study, and we make 4 different samples with a different temperature, and these 4 samples represents 4 different stages of this entire fabrication. Now, when we did the XPS study, and we found that and that was a platinum-based metallic glasses, which has 4 elements: platinum, copper, nickel, and phosphor. And we saw that platinum does not change, the copper neither, but the nickel actually changes. And nickel changes from nickel oxyhydroxide. And these actually hydrophilic in nature, so that's why the contact angle decreases. But the good thing is that we found that at 260 degrees Celsius and S-cast and 260, there is no nickel oxide formation. So we decided to carry on our fabrication at 260 degrees Celsius to avoid the formation of nickel oxide. And so we developed a technique. The problem is that, as I showed before, we do etching, but we cannot do etching for this study. So we decided what are the alternatives to detach this metallic glass from this mold. So if you pull at a room temperature, it actually broke. It breaks, the mold breaks. So basically, this is the result. These pillars are embedded in the mold. So, and if we pull, so if we actually developed a pulling technique, so we place metallic glasses and we pull it at when it is super cool liquid state, when it is soft, but we saw there is some different structures actually created. And we study some rheology, or it is called like how the strain rate affect the yield strain. We found that if we pull if the higher strain rate, the metallic glasses actually it acts like a solid. And what we decided, we'll press slowly and then pull very fast so that my structures remain intact. And now we have seen when we pattern our metallic glass with this method, we have seen the changes in contact angle. Okay, so we found that it transformed from Wenzel model to the Casey-Baxter model. What is the Casey-Baxter model is there is some air, and this air acts as a cushion and does not allow the water droplet to touch the base, this base. But again, if your spacing, we call the pitch, if the spacing actually goes higher than water actually touches the base, then when this water touches the base, it moves to the Wenzel model. So the message is, if you can control your spacing, you can transfer the wetting state from Wenzel to Casey-Baxter. Once you transfer the wetting state to the Casey-Baxter, you will get a higher contact angle. So we study with the effect of topography with aspect ratios and effect of different type of topography like triangular holes, honeycomb, and we have seen a significant change in result. Now, the next we move to mimic what is actually in the lotus leaf. As I said, the lotus leaf, you have two-tiered pattern. You have micro pattern, and then on the top of that, these nano flecks or nano vecks. So the question is, can we do multi-tier pattern? We call hierarchical pattern. So we start the metallic glasses molding with the small features, and then use that one against a mold which is a larger feature, larger holes, and we ended up this multi-tier pattern. And how many levels we are able to add, as long as the metallic glass can be thermoplastically deformed. So this is some pattern, as you see, and this is a honeycomb pattern, and it has some nano rods, nano fur on the top of the wall, and we are able to see in that it shows petal effect. And if you just flip your substrate, this droplet actually hanged instead of rolling. It can hang. So we have published these in the 4 different journals. Now, so this is the summary of this wetting study. The topography alone turns PTMG hydrophobic, and single-scale micropattern converts hydrophilic platinum metal glass to hydrophobic, and the hierarchical or multi-tier pattern actually enhance the superhydrophobicity, and the platinum-based metallic glass shows petal effect. Now, now let's move to the next part of my talk, and now I'm going to show you how can we actually transform or utilize this additive manufacturing in device miniaturization. miniaturization. So this is a one example. So for example, this is a Mark I computer, and that is, as you see, how big it is. It it mass is 4,500 kg, and this is a pocket laptop, and its computing power is more than this Mark I computer, and but its mass is only half kg. So as you see, we saw a revolution in electronics, in the solid state physics, and the device actually, miniaturizes a lot. And similar trend is observed in the satellite. So this is an Earth observing satellites, which has again 2,500 kg, and this is a nano satellites, which is only zero point 0.1 kg. Now there is another satellites, and this kind of nano satellites or small satellites are now in action in the space. So this is a there is a satellite we call Cubesats, and this is the critical dimensions of the Cubesat. So 10 by 10 by 10 centimeter is less than 2 kg, and these satellites actually are using Earth observation and amateur radio. And one of the significant notable mission is this Cubesat actually is used in Mars. So basically, what they do, they use this small satellite as a communication device. And for example, the Mars is very way from the world. So to transmit your signal, you need some intermediate station where it can capture your signal and transfer to the next transmitter. So the Cubesat is used in this purpose. So since everything gets shrinks, like your satellites get smaller, so that means that its propulsion system needs to be smaller. So there are three different type of propulsion systems actually has been developed for this kind of small satellites or CubeSats. One is called cold gas thruster, electric propulsion, and chemical propulsion. And the electric propulsion has multiple, like ion thruster, pulse plasma thruster, electrospray thrusters. So the idea is that, think about your car. Your car has a lot of moving parts. In a car is an engine. It has a lot of moving parts. It has a pump. It has a gear and everything. So when you want to shrink it, it's very challenging to shrink because you cannot make a pump in the micro scale. It's very challenging. So the idea is that, is there any other way we can eliminate those moving parts so that the fuel from the reservoir automatically transmit to the thrusters, and this thrusters gets fired and the entire thing moves. So one of the technologies called that technology, electrospray thrusters, we call Ionic Electrospray Propulsion System, IEPS. The idea is you have a reservoir and you are going to use some emitters. Those are porous, and these emitters, because of the capillary, from the reservoir, the fluid actually diffuse through these emitters, and you have a high potential differences, and these emitters, the liquid actually sprayed because of the electrostatic pressure. The liquid actually sprayed on those extractor, and as a result of this, as you see, this is a positive ion actually extract, and as a result, it gives a thrust due to Newton's law. Now, this is a ionic thrusters based electrostatic propulsion. As you see, it's less than it's a quarter, and these are the thruster, These are the tips. And so our goal is to making a material so that we can make those thrusters. So we developed a porous material, and these porous materials is such that they are bicontinuous. That means that it can actually, liquid can flow. And these are the some, we did some lithography to make the mold. And these is one of my molds. And uh, we press this paste into this mold, and it gets cured, it gets solidified. Then we get rid of this mold, and these is my thrusters. And this, if you see, this is the tip, and this is the port. Basically, the liquid actually will come from these pores. And we did some FIB study, and we cut a single thruster. We saw the morphology, the base and the pillars are the same. So, and we do some confocal study. And this is the one actually I'm going to on this video, as you see. So this is the plume, this is the pattern. And when I apply the electric field at the beginning, basically there is some fume. These are some ion electrospray. So the idea is this: you have a magnet, you have upper high voltage, and the liquid actually diffuse through this matrix, which is the tip. When you apply the high electric field, you will see this electrospray. So these are some future research I was planning. One of the ways that the multiplex electrospray to for the coating, and I have some research idea which I would like to pursue. The one of the things is that how this kind of composite flow to a narrow hole. So for example, if this is a polymer composite, if you press against a mold, it will fill very nicely. Now if you have some particle, it will still fills very nice, fills the hole very nicely. But the question is that when you have these holes gets narrow, there could be this scenario, or there could be that the particle actually block these holes. Only the liquid can flow. So we can do some study. We can do the simulation if anyone is interested in. If you know the ComSource or any other software, I'm not in this computational guy, but I would like to collaborate with someone who can actually simulate this to see what is the critical size of the particle that will allow the homogeneous flow instead of phase flow. So this is desirable, this is not desirable, this one. But I want to see that what would be the size of the particle, or really the whole size that will allow these things. So this is an example of that. As you see, these are micro holes, basically the micro holes, and you see the particles. But if you go to the nano, there is no particle. Actually, that's why this is the limit. So you cannot do the nano pattern. You can do the micro pattern, but you cannot do the nano pattern. So can we increase this limit? The answer is I don't know. So we need to see, we need to do the simulations, and then we will do our experiments. Now, the other research idea I want to show, let me give a minute. Let me try other things. This is from a newspaper. Okay, so this is from the New York Times, and as you say, this is a classroom, um, and in the United States, it says that open window is very effective to mitigate the coronavirus transmission. So think about a classroom. This is the previous one setting, and now this is the current classroom settings. And there's a social distancing, and the students are maintain a 6 feet distance. Now, and these are the air flow in a room. The think about one student is infected, for example, these students, and his aerosols, his breathing actually spreads to the room, and it spreads to all over. This aerosol is all over to the room, and it says that 3% of every students or every persons in this room actually inhale 3% of his aerosol. Now, but what happened when you open the window, and this it still is aerosol actually moves, but the concentration is very less. So open window is one of the key features to improve the high quality, to improve the indoor high air quality. Now, the problem is not every schools or every building has a window, right? Especially if you leave a building where is a room inside, you don't have any window. So what we decide with the company to make a system, for example, these blower, so that it can actually blow air, and it will create a air circulation. Let me show the simulation. This is the simulation. So you have an inlet, you have an outlet, and you're spraying the fresh air, and this fresh air actually create these two collides, and they are separating. They are not mixing to each other. Now, if somebody sits here and somebody sits here, and these air flow, different air pattern actually would not allow to inhale each other aerosols. So as you see, these aerosols will go, it will stay here, and his aerosol will stay here. So I want to do a simulation. I have done this simulation, this background simulation, but how the aerosol will, what is the velocity vector of this aerosols particle? That could be a very interesting research. And if any one of you are know the fluent, you can contact with me. We can discuss about this particular project. Now, the next move to the next topic of my talk. What is the skill set for research? As an experimentalist, I will talk only about the experimental skill set. I'll not talk about what the simulation and theories requires, because that is not my expertise. Now, so I would say that design of experiments, setup, and observation and analysis, and modeling the data. So today I'll only focus the design of experiment setup. And the first one. So I'm giving in one example. I'm instead of talking about like a abstract ideas. So this is a instrument called film matrix. What it does, it can measure the thickness of a thin film, if this film are micron scale. Okay. Now, this instrument actually we used in our postdoctoral during my postdoctoral research, and my supervisor only brought these this probe, as you see in the red box. He didn't buy these things, this stage. Okay. Now, the problem of this, if you don't have the stage, you can move this manually, and it can only, you know, for example, you need to do it, you need to measure the thickness manually. Like maybe 1 hour you can measure like 20 or 30 spot. But what he did, he assigned his students who build this stage, and now this stage is automatic. It can move like a few micron. Now, instead of a point, we were able to measure certain area, uh, within a couple hours. So it's a completely automatic, and just stage move few micron. It covers a very large area, and we got a lot of results. So this kind of like expertise is very essential for the experimental result. You need to build a experimental setup or device to for the data acquisition. Now this is another example I'm giving. This is an I have started this work at the end of my postdoc. We are developing an ultra high vacuum system to test the ionic propulsion system. Now, this system, it costs around $50,000. So I buy each and every part from the vendor, and I need to design this. And I couldn't finish it, but I wish I could have more electrical and electronics knowledge. Then that will actually expedite this process. So what I would say that nowadays you need to, even though your field of study is mechanical, chemical, or whatever, you should have a very sound knowledge of software like a MATLAB, LabVIEW, and you should be able to interface the software with the hardware by using a DAC, data acquisition system. TA has a data acquisition like an Arduino small data acquisition system, and this kind of technique is so useful. And I think many countries like China, and Iran, and some Indian folks are very good in instrumentation and control. And nowadays, the instrumentation and control are the key for building the experimental setup. And many research actually in the graduate students spend 1 or 2 years just to build up their setup. And if you and many students actually fails because they have a very little knowledge of this instrumentation and control. And you should have a knowledge of CAD modeling, and also some machining experience, sometimes helpful. But I would say this instrumentation and control is the key. So this is the last part of my talk, transforming idea to publications. And I know many of you have done this design projects at the fourth year thesis. Is it possible to do a systematic study of those topics? And it could be very small. It could be a very small idea, but you can publish a journal. So I'm giving you 2 examples. Now look, this paper is published in 2000, I guess 10. And so in this paper, what they did, they and 2010, that time actually smartphone was not that popular. So the people has this kind of camera. So the authors actually build up a experimental setup, very simple experimental setup to measure the contact angle. Now, uh, many researchers need the contact angle measurement, and those equipment, if you want to buy commercially, is $5,000 to $10,000, and sometimes PI cannot afford. But he made this instrument, this measurement system, I would say less than $500. Okay, so and he did some software manipulation, how to measure the contact angle, and then he published this in a journal. And it's a small words, but it is very useful because people copied this system in the lab. Actually, I copied this when I'm a PhD student. I copied this system. I just made my own contact angle measurement system. Just copy this paper, and now there's the idea actually evolves. Now in 2018, by this time everybody has a smartphone, and you no longer use the camera. So some folks said, hey, we will do these things but with a smartphone. So these authors, they build up a system, similar system, but this time with a smartphone, and they showed how accurate their data. They provide some experimental data, and they publish it in a paper. So is it possible to small idea to 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 do a systematic study and publish it? Now that's all. And thanks for your time and attention. And I would like to take any questions you have.
Thank you, sir, for your valuable speech. Hope that it would be helpful for all of the participants. Now I will read out questions from the comment box. We are also providing the StreamYard link in the event description. You can ask questions directly. So, one question. Uh, Shahriar Ahmed, for materials engineering study, which software is most important?
I think it depends. So it depends what kind of study you want to do. So I didn't use any software. So I'm an experimentalist, but nowadays the many material scientists use MD simulation, molecular dynamics simulation, to uh, to study the interaction and many phenomena in the atomic scale, like addition, cohesion, and friction. And also this they use MD simulation to see the mechanical behavior at nanoscale. So I would say MD simulation, but there are a lot of other materials. The other one, the DFT, they also use the DFT to uh, to study the crystal structures the and crystal structures related properties.
So I think also.
So if you have any further question, if you want to contact with me, you can email me here. You can email me here. Also, you can email to my official email. Okay. Okay. If is there any other questions?
So no question, and our program session is very good. Some comments are very positive side. MD Salvation, he said very informative discussion. Thanks, Dr. Molla Hasan sir, for managing time to share your deep knowledge. And Rabul Islam sir, he told wonderful session. Shahriar Ahmed, very hard topic for me, but get explanation, sir. Thank you.
Okay. So okay. So should I leave the session?
So thanks again, sir, for your valuable time. Also thanks to the audience for your participation.
Okay.
Our next research idea series, 5th, will be held on 11th April 2021. To get update of your activities, follow our page, join our group, and subscribe to our YouTube channel. We are happy to inform you that we are now a family of more than 23,000 members, including group member and channel, within 9 months only. Stay with Gobashikota Chai, be researcher BD, and invite your research enthusiast friend to our platform. Wish you all success and good health. Allah Hafiz. Assalamu alaikum.